6. So if we finish all the questions I have early, that's it for today. And if we don't get through them all, then we'll try to probably do some more of these Monday. I have no idea what time we're going to get done today. But I put several things on here. So do you guys also have all this stuff on your slides as well? I put these on Blackboard, right? These review slides. Okay, you should have these. All right, let me pull the chat up. Okay, good deal. All right, well, let's go through this. So I actually have a poll question for this first one. We're going to be just doing chapters 4, 5, and 6, and it's kind of a random order here. I don't think I put things in order. I might have, I don't know. But this first question is from chapter 4 content. So let me pull the poll up, read the question. I'm going to launch the poll. Molecular compounds. So we talked about ionic compounds. That was exam 1. And chapter 4 is where we got into molecular compounds. And I want to know, did we say these form between metals, nonmetals, or one of each? Okay, think about a molecular compound and how it's different from an ionic compound. This is one of the first things we talked about in chapter 4. All right, we're almost all the way there. 5 people left. All right, get your vote in. All right, you should be able to answer this by now, so I'm going to stop the poll, share results. So most people said, 70% said 2 nonmetals, and that is correct. Okay. Now, again, that is not, I say the word usually here because there are times where different bonds, I'm going to remind you of polar and non-polar bonds, okay? If you remember the chart, we can classify different bonds as polar, non-polar. Those are both covalent. And then we have an ionic type of bond, okay? Things that are ionic bond in nature, those are ionic compounds. So usually it's 2 nonmetals there, okay? All right. So you should have picked that one. There we go. Okay, I'm going to close this poll. All right, read the next one. Element X, I have a poll for this as well, has 5 valence electrons. How many bonds will it form in a Lewis structure? And then what rule did we write down? So the only part that's on the poll is that first question there, not the parentheses part. Let me find my poll. Okay, so there's a poll. Put your answer in when you feel like you have it. I've been getting lots of questions. I had Zooms yesterday with multiple students about Lewis structures. So how do we determine how many bonds an element will form? I'm going to flip over to this was our chapter 4 lecture. Let's go to this slide right here. Is the slide where we talked about this, okay? So I said, when drawing molecular compounds and when figuring out how many bonds something will form, here's some good questions to ask yourself. All right, we're about 60% voted. How many bonds? If it has 5 valence electrons, I guess I need to go, I typed the question into the poll as well. So you have an element with 5 valence electrons, how many bonds will it form in a Lewis structure? All right, get them in, get them in. All right, I'm going to end the poll. Share results. So 75 almost percent of the class said 3 bonds, and that is correct. Let's think about this. Let me go back over to my slide right here. So if we have 5 valence electrons, remember we said the number, actually let me go back. Right here, the number of electrons that an atom needs to achieve an octet is equal to the number of bonds it will form. So if we have 5 plus what gives us an octet? An octet is 8, so 5 plus 3. So this is the number of bonds, okay? This is easy math. You can always do this if you have questions, all right? And then also, let me scroll down. This figure right here, remember this from your textbook? It tells you, so if you're 5 valence electrons, your main group 5, it tells you that they normally form 3 bonds. And you'll have access to your lecture notes on the exam, remember? So that's the answer here. What rule did we write down in class for questions like this? Well, it was that one in red. Every time you share an electron, you gain an electron, okay? And you use that to guide you to figure out how many bonds things are going to form, okay? Any questions there? So we talked about the octet rule and how electrons are shared, and therefore how things will form bonds as a predecessor before getting into Lewis structures, okay? Another thing we talked about was diatomic molecules. I think I have a poll for this too. So read this next question. Let me launch the other poll. And here's the deal. There may be more than, also this is a typo. This should be E, okay? And I think there may be more than one correct answer. So you just pick one that you know is correct. There might be more than one. How's that peanut butter, Abby? You want some, Jackson? Diatomic molecules are so important, and I think in chapter 6 y'all were reminded a little bit of how important they are. You need to know what elements are diatomics and what are not, especially when you calculate molar masses and things like that for chapter 6 stuff. Wildly different answers on this poll, wildly. I'm glad we're asking this question. Okay, everybody almost voted, 27 of 30. All right, in the poll. Dang, who's providing breakfast? Everything's better with food, guys. Y'all know that. Sorry, my screen died. Okay, let's look at this. Share results. What is not a diatomic molecule? So we've got sulfur, oxygen, fluorine, phosphorus, and hydrogen. So most people said D, that D, phosphorus is not a diatomic molecule. And you are correct. That is not a diatomic molecule, okay? But then numbers were split between everything else. So let's look at this. Go back to chapter 4. Where did I go over diatomics? Right here, this slide. You have this slide from chapter 4. Okay, diatomics are elements that naturally exist as 2 bonded atoms and hydrogen, and then remember they make a 7, okay, on the periodic table. Nitrogen, oxygen, and your halogens. These are your diatomics. So which one, if we go back to our question, is not one of those? Sulfur. Sulfur is not a diatomic. Okay, so phosphorus and sulfur, but the other ones are. You have to remember this. When you go to calculate the molar mass of any of the diatomics, you have to remember there's 2 atoms involved. If not, you'll miscalculate the molar mass, and then problems like what we worked for chapter 6. Someone said I read the question wrong. You were picking the ones that are diatomics. Is sulfur usually SA? I feel like I remember that from high school. Sulfur can exist as SA, Caroline, but that is still not a diatomic. So, okay, I'm gonna close this down. All right, let's read the next question. We're still on the octet rule here. I really want you guys to remind yourself of this before we just jump into Lewis structures, because how atoms bond together and form Lewis structures all depends on how they achieve an octet, okay? So let's name 3 elements that are an exception to the octet rule in a covalently bonded molecule. How so? You can type it in the chat, you can unmute. There's more than 3, but someone tell me 3. Or someone tell me 1. Kathleen, thank you. Hydrogen and helium are 2 automatics. Okay, these, if we draw a picture, there's the nucleus, there's the first energy shell. And remember, these only hold 2 electrons, not 8. Okay, so they're an exception to the octet rule because they're full when they have 2 electrons in the outer shell. So those are exceptions. Can someone name another one? Kathleen says phosphorus. Yes, phosphorus can be an exception. Okay, phosphorus has 5 valence electrons, main group 5. Phosphorus can share all 5. Okay, it doesn't normally do this, but it can share all 5. And we drew a picture of this in class. If it shares all 5, let's draw it involved in 5 bonds here. PCl5, that's a real molecule. So we have 5 chlorines here. I'm not going to take the time to draw in all the lone pairs on the chlorines. How many electrons does phosphorus claim? Remember, every line representing a bond is 2 electrons. And every time you share 1, you quote gain 1. So phosphorus here is claiming 10. Thank you, Jenna. 10 electrons, okay? So that's an exception. It exceeds the octet rule. Sulfur, Jenna wrote sulfur in the chat. Sulfur is also an exception. Sulfur has 6 valence. Sulfur can share all 6, and when it does so, it has 12 electrons, claims 12 electrons. So that far exceeds the octet rule. How about this one? Nobody has said this one. What about boron? Every time I say boron, I think of like James Bond. One of his enemies was, I forget his name, but it sounds like boron to me. Boron, where is boron? Let me go back to this. Right here. Boron is main group 3. B, that's boron. Boron has 3 valence electrons. It's in main group 3, 3 valence electrons. So boron can share all 3. All right, let's draw a picture of that. Here's its 3 valence electron dot structure. If it shares all 3, let's say in bonds to hydrogen. Sorry. Okay, let's say we got something like this. Remember, we got bonds, 3 bonds here. How many electrons does boron claim total once it shares all 3? It only has 6, right? So it did not even get an octet. Okay. So boron's an exception here. It doesn't have any more to share, so it can't get any more. So it's also an exception to the octet rule because it can only end up with 6 total, not 8. Okay, but it's stable as can be that way. All right. So now we're going to do some review with Lewis structures. So let's start with number 1. I want you to take a minute. I'm gonna flip over to the rules. I'm gonna remind you of the rules for drawing Lewis structures really quick. They are right here. First thing you do when you get ready to draw a Lewis structure is you calculate the total number of valence electrons. Then, rule number 2, you're going to start connecting your atoms. Draw a line, or a dash, whatever you want to call it, between the atoms that you think are connected. And remember, each line represents 2 electrons. Rule number 3, see how many electrons you still have left to account for. And you start putting them as lone pairs on your perimeter atoms, okay? Your non-central atoms, any atom connected to a central atom. The only exception here is hydrogen. Hydrogen should never get lone pairs, okay? So if you have an oxygen connected to your central atom, or chlorine, or an atom like that, you'll put lone pairs on it, but not hydrogen. Rule number 4 is any remaining electrons, so count up your electrons again, anything left you're going to put as lone pairs on the central atom. But lastly, if the central atom does not yet have an octet, after all the electrons have been assigned, you're going to pull lone pairs from those non-central atoms and start making double bonds to your central atom. The greatest example of rule number 5 is if you draw out CO2, carbon dioxide. You follow these rules step by step, 1, 2, 3, and you realize you get to number 5 and your central carbon does not yet have an octet. So you got to pull lone pairs off the oxygens and you'll have 2 double bonds in a molecule of CO2. All right, let's practice this though. There's the rules. Let's start with number 1. I'm going to give you all a second, start adding up the valence. And we may get different valid structures here. There's probably more than one way to draw this. Okay, I got 32 valence electrons. Did y'all get 32? All right, so start connecting your atoms here. Remember, carbon can be a central atom and oxygen can be a central atom, but fluorine and hydrogen cannot. They cannot. They can only have one bond. All right, I'm going to start trying to piece these together. I'm going to put my carbons, I like to do this in black. Okay, that's what I have so far. Anybody have anything different? Anybody piece it together differently? All these perimeter atoms are pretty much interchangeable. So if you drew your fluorine like over here, you know, that's fine. You can move around the perimeter atoms as long as they just have one bond. You could also have drawn something like this. Okay. Something like that. Okay, what's wrong with my structures though? What am I missing? 3 lone pairs to the fluorine. Thank you, Kathleen. You've got to make sure you can, if you counted up all the electrons here, you'd be 6 short. That's because halogens, so not just fluorine, but chlorine, bromine, iodine, they always have 3 lone pairs. So now if we count up our electrons, remember every line is 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and then 6 more on fluorine adds up to 32. Okay. All right, any questions on that one? Feel good? Okay. Number 2, there's a typo. I caught this last night, so let me take care of our typo. Instead of having the parentheses right here, I'm going to move our parentheses just to around oxygen. Okay, so pretend there is no parentheses right there. So it should be C parentheses O H CH2 C CH 3 and then NH. I think that should be correct. Hopefully so. So let's start. Let's start dividing this into groups. Remember, you read this left to right. Okay. Does the order not matter? It would count mine wrong in mastering. Olivia, are you talking about the structures here on number 1? Yes. Okay, is that also about the Lewis structure dry lab that we did? That's the only one where we've drawn them. So I'm assuming that's the one you're talking about. Or like the homework as well. Did you run into issues with that on the homework? I know you had to draw some Lewis structures on the homework. If you're talking about the Lewis structure dry lab, I can look into that. Okay, if you miss significant amount of points for getting things wrong, shoot me an email and tell me the question that you're asking about, and I'm more than happy to look into that and look into your grade. Okay, thank you. All right, so let's divide this into groups, and then we'll connect the main chains, and then we'll put the branched atoms on. Okay, so group number 1 is going to be my carbon is my main chain, and so I'll draw a line right before the next preceding main chain. Okay, so the next preceding main chain element is the next carbon here. Okay, then we have the CH2 group, and then we have another carbon, so I'm going to draw another line. And then we have nitrogen can be a main chain. Nitrogen, oxygen, anything that can have more than one bond can be in your central main chain. Okay, so let's start trying to draw this. So we have a carbon number 1. So this is going to be carbon number 1. And we have an oxygen in parentheses. So what should I do with that oxygen? What does it mean when it's in parentheses?
Do you branch it off?
Yes, you branch it up or down. So you're not going to draw oxygen like this in the main chain. You're not going to do that. This one's in parentheses. Sometimes you can do oxygen that way if it's not in parentheses, but when it is in parentheses, we are going to branch it up or down, does not matter, up or down. And oxygen should have 2 bonds always. And how many lone pairs? 2. So I'm going to put my 2 lone pairs. Remember, a pair is 2 electrons. So 2 pairs is 4 electrons total. And then we also have this hydrogen right here. This hydrogen is also branched off that carbon. So we're going to draw hydrogen. All right. So now carbon number 1 is connected to carbon number 2. So we'll extend our structure left to right. I see that carbon number 2 has 2 hydrogens, so I'm going to connect those up and down. Carbon number 2 is connected to carbon number 3. There's carbon number 3. And now we have a CH3 group in parentheses. What does that look like? You had one of these on your Lewis structure dry lab. So it's in parentheses, which means it's branched. So you should have a carbon with 3 hydrogens branched off. Okay. And then the last group is a nitrogen here. So we've got a nitrogen with a hydrogen branched off of it. Okay. Now, if we just stop there, we're not done. We're missing some things. Okay. I need your help to figure out what are we missing? How do we complete this structure?
A lone pair needs to be over carbon, right?
Put a lone pair on carbon?
Yeah.
What do y'all think? No, don't put lone pairs on carbon. Don't do it. Do not do that. Nope, nope, nope. Carbon has to have an octet. Let's look at this carbon right here. I like what Jenna just said, but before we read what she said, let's look at carbon number 3. Does it have an octet? Remember, every bond represents 2 electrons, so it only has 2, 4, 6. It's not satisfied. It doesn't have an octet. We've got to give it another bond. Okay, and we can't give it a lone pair. It's got to be a bond. So, what can we bond it to? She said double bond it to the nitrogen. Also, look at nitrogen. Nitrogen is way short. Nitrogen only has 4 electrons that it's claiming. Okay, so we're going to give both of them another bond. Now the carbon here is satisfied. We're good there. Nitrogen's not done though. Nitrogen only claims 6 electrons, right? 2 electrons here, 2 electrons here, 2 electrons here. It does not have an octet. What can we do with nitrogen though that we cannot do with carbon? And I said give it a lone pair, and that's correct. Okay? We can give nitrogen a lone pair. So when it's all said and done, let me clear it up here. This is what your structure should look like. You got a double bond. Those double and triple bonds are tricky. It doesn't that's what you have to discern when you're drawing out these Lewis structures from a condensed structure, is where you have a double or a triple bond. I promise I'm going to give you one like that on the exam. All right. Questions on that? Oh, we did not count the electrons here, but you totally could. So we have 1, 2, 3, 4 carbons. Let's make sure our electron count is correct. So we have 4 carbons. Each one has 4 valence, so that's 16 from carbon. We have 1 oxygen that has 6 valence electrons. Hydrogens, I see 1, 2, 3, 4, 5, 6, 7 hydrogens in our structure. Each one has 1 valence, and then we have a nitrogen. 1 nitrogen, 5 valence. So total 11, 7, 18, and 16 is 28, 34. That's what I got. So I'm going to count real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32, 34. I counted 34. Okay. So just always double check. If you do not get your count right, then you know you're off somewhere. Okay, let's do another practice. Number 3 looks hard. We got lots of carbons, lots of hydrogens. We've got lots of oxygens here too. And this is not a condensed structure. Okay, so how can we go about this? First, add up your valence.
We can't see what you're doing.
My screen must be lagging. I see that it's lagging. Thank you. Sometimes if I stop share and reshare, it'll catch up. Can you see now? Okay. Thank you, Allison. Okay, so I'm zooming in on number 3. I was just adding up the valence here. I got 36. So someone shoot out an idea. How should we start to draw this? What's one thing we could do? 3-carbon chain. Okay, Kathleen says, let's just connect our carbons. And then we got a lot of oxygens here. Okay, so there's so many different ways we could do this. I'm going to draw a couple different structures. You could, then connect your oxygens like this, right? This looks crazy. This last oxygen will have to have another bond on it. So we could put a hydrogen there. I'm going to see if this is a valid structure. It may not be. Because look, I got to put a lot of carbon or a lot of hydrogens on these carbons. I don't think this is going to work. If I start just putting hydrogens over here, I'm going to run out of hydrogens. We can only have 6. And right now I have 4. So if I do this, I'm out. I got 6, but look, this carbon's not satisfied. It's got to have 4 bonds. If we counted up all our electrons, even if we put lone pairs, I think we're going to be short. So this is not the correct structure. Okay, so let's try something different. Let's go back to a 3-carbon chain. I think that's an okay move. What if we did like OH groups off these carbons? I'm just putting them random places. We know that each oxygen gets 2 bonds, 2 lone pairs. So all my oxygens are satisfied. So far, I have used 3 hydrogens, okay? And what if I put 3 here? Okay, we're getting close, but we've used up all of our atoms, okay? Now let's double check, are all my carbons satisfied? My hydrogens all have 1 bond, my oxygens all have 2 bonds, 2 lone pairs. Let's see, does every carbon have 4 bonds? Well, this carbon has 4 single bonds, so we're good there. Check. What about this carbon? Uh-oh, this carbon only has 3 bonds. What about this carbon? That carbon only has 3 bonds. What can we do?
Can you remove a hydrogen from your the 3 bonded carbon and then double bond to the C's?
Anybody have a solution? You could remove a hydrogen and do that, but what about something that's even easier? I think we could do something where we don't have to move any of our atoms.
Just double bond the 2 carbons at the end of the chain, correct?
Jackson says, Jenna says double bond carbon and oxygen, but Jenna, if I do that, my oxygen will have 3 bonds. So I can't do that. But Jackson said double bond the 2 carbons that only have 3 bonds. So he's saying right here. What do y'all think about that? Now, does this carbon have 4 bonds? 2 single bonds and a double bond? Yes. What about this carbon? 2 single bonds and a double bond? That's 4 bonds. We're good. Okay. So this is literally my strategy with Lewis structures. If you're wondering how I do them, sometimes it's trial and error. There's so many other different ways you could probably draw this structure. Okay. You could probably, instead of connecting all 3 carbons, you could probably put oxygens in between the carbons and things like that. Okay, but I don't want to take too much time on this one structure because I want to get to other things as well. All right, let's double check. Do we have 36 electrons? I'm just going to count really quick in my head. I counted 36 between all my dots, all my lone pairs, and all my bonds. I counted 36. Okay, any questions on that one? That one was a little more tricky. Okay, and again, the trickiest thing is figuring out where you have a double or a triple bond. That's the hardest part, okay? All right, number 4. So we got 2 carbons here in this structure. I'm adding up the total valence first. So 2 carbons, each one has 4 electrons. That's a total of 8 hydrogens. We've got 4 hydrogens in our structure. They all have 1 valence. And we've got oxygen. We've got 2 oxygens. They both have 6 valence. So 24 electrons in this structure. Okay, so we're going to have, this looks more like a condensed structure, right? Here's how I know that. We've got this CH3 group. You know what though, if I were giving this to you on an exam, there's something about the structure that I realized I should put in. One of these oxygens should be in parentheses, okay? Because it's going to be misleading if it's not. So, all right, now that we made that edit, let's draw this. So we got a CH3 group. So just draw your CH3. Then that's connected to another carbon. So we got carbon number 1 and carbon number 2. We got an oxygen in parentheses, which means what we did over here is we branched this oxygen off of that carbon. Okay, so we're going to do the same thing. When we have an oxygen in parentheses, you branch it. It doesn't matter if you branch it up or down. And oxygen gets 2 bonds, 2 lone pairs always, whether it's 2 single bonds or a double bond. Then we have this OH group. So, and it's branched off of that carbon, okay? So now, some of you might be tempted to do this. Why is that wrong? I put an oxygen and a hydrogen on, but that is not right. How many bonds are on this carbon? Seth said too many. Yeah, 1, 2, 3, 4, 6 bonds. Carbon can never have more than 4 bonds. Okay, so let's try again. It's got to be an OH group. We're going to keep these bonded together like this. Okay, now if you look at the second carbon, I have 1, 2, 3, 4 bonds on that carbon, so that's good, and everybody's satisfied. Then if we go back and count, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, so we're good. Okay, questions there? All right. That's just some practice with Lewis structures and condensed structures. You'll probably have 3 or 4 structures. I don't know. I've never done an exam like this fully online, so I'm going to have to toggle with what's easy to grade as well. But you'll definitely have some Lewis structures you have to draw, okay? And condensed structures you'll have to read. All right, next question. Which of the following molecules would have trigonal planar geometry? So after we talked about Lewis structures and condensed structures, and we're still in chapter 4 here, we did geometry. So I want you to look at these. I don't think I put this on a poll question. Which one would have trigonal planar? First off, what is trigonal planar geometry? How many bonds on our central atom? I don't think I have. Yeah, I don't have the, I don't have that table. Let me show you what table I'm talking about really quick. If you forget how to go about this, let me download that lecture. It's in our chemical reactions lecture. That's fine. There we go. Now I want to remind. No, it's not. No, it's not. It's in this lecture. It's right down here. Forgot. This is what I'm talking about. This table right here. Okay, this is still chapter 4. Sorry. I don't know what I was thinking. Okay, trigonal planar is right here. Oh, pencil. So we are looking for 3 bonds, 0 lone pairs on our central atom. That is trigonal planar. All right. Right there. So carbon with 4 bromines is going to look like this. Okay, and then all those bromines would have 3 lone pairs. So is that trigonal planar? No. Okay, Kathleen says BF3. Let's look at BF3. Boron, remember, we said boron's an exception to the octet rule. Boron can only have 3 bonds, okay, and here it's bonded to fluorine 3 times. So does that match? 3 bonds, 0 lone pairs? Yes, it does. That one is trigonal planar. Okay, what about this one though? That one looks similar. We've got phosphorus, 3 bonded atoms. Would that one be trigonal planar? Let's draw it. How many electrons, valence, does phosphorus have? Phosphorus is in main group. Kathleen said it would have a lone pair. Phosphorus is in main group 5, so it starts out with 5 valence like this. It shares the 3 that are not paired. The 3 lone single electrons that are not paired up, those are going to be bonded to your chlorine atoms. Okay, and then those chlorines would have a bunch of lone pairs too. Remember, you do not count the lone pairs on your non-central atoms. So just because chlorine has lone pairs, we don't factor that in when we're naming the geometry of phosphorus. Phosphorus here has a lone pair. So what geometry would this molecule be? What geometry would phosphorus have? What does this match? 3 bonded atoms and 1 lone pair. Jenna, you're very, very close. Just pyramidal will suffice. Okay. This one is pyramidal. Okay. All right. The others are not, so we're not going to waste time drawing them. Questions there? All right, here's another geometry question. Which molecule contains only 2 unshared pairs of electrons? Which molecule contains only 2 unshared pairs of electrons? And I'm talking about in the entire molecule. So you're going to draw these out. Start with water. Water is oxygen with 2 hydrogens. And what do we know about oxygen? Get 2 bonds, 2 lone pairs. Would you look at that? The first one we drew. 2 unshared, so 2 lone pairs essentially. An unshared pair is a lone pair. So water fits the bill here. Let's look at these other ones though. Nitrogen with 3 hydrogens. Nitrogen is just like phosphorus. It starts out with 5 valence. 3 of those will be bonded to the hydrogens, and we have only 1 lone pair here. So not ammonia, not NH3. BeCl2. Sometimes I forget where beryllium is. Be. Oh, it's main group 2 right here. Okay, first off, this is not even a covalent molecule. This is ionic. This is a cation and an anion. So we're not sharing electrons here. All right, and MgO, guess what? That's a metal and a nonmetal. This is ionic too. We're not sharing electrons here. We're trading. All right, so water is the only one there. Okay, we're still in chapter 4. Any questions on that before we just move on? All right, let's talk about polarity. We got polar bonds and we got polar molecules. So I conveniently put this electronegativity chart down here for you guys because you're probably going to need it on these questions. So the question is, which bond is most polar? Most polar. So you need to calculate electronegativity differences. So the first one is CBr. So let's find carbon is 2.5, Br is bromine is 2.8. So we'll do 2.8 minus 2.5. This was bromine, this was carbon, and we get a difference of 0.3. I think I put the table down here too. 0.3, this is just nonpolar covalent. So guess what? That first bond's not even polar. Nonpolar. Okay, boron and fluorine. Boron is 2.0, fluorine is 4.0. Boron 2.0, that should be a chemistry show. So we got a difference here of 2. So this is technically ionic. Technically, even though boron here is a metalloid, not a metal, that's an ionic bond there. Because if it's 2 and above, it's classified as ionic. Okay, lithium and fluorine. Lithium is 1, fluorine is 4, so you should have 4 minus 1 is a difference of 3. That's definitely ionic. It's very ionic. Okay, so what about phosphorus and chlorine? Phosphorus is 2.1, chlorine is 3.0. So we'll do 3.0 minus, what do we say, 2.1? The difference is 0.9. This one is polar, okay? Now, I'm sure some of you are thinking, well, you said the most polar, okay? And I would want to, if I ask this on an exam, I would definitely clarify. Because this one is nonpolar, oops, nonpolar. And we have 2 ionic. We only have 1 that is polar, so I would want you to choose PCl. It's the only one that's polar, so that one's the most polar. Okay, so that's bonds, polar bonds, and that's just an example, remember, of how you calculate bond polarity. I love to ask questions that are list the elements in order of increasing or decreasing bond polarity. And if I gave you a question like that, if I said list these in order of increasing polarity, how would we order these? Ionic bonds are so polar that they're beyond polar, if that makes sense, okay? So if I said list these in order of increasing polarity, you would start with the one that's the least polar. That's going to be A, CBr. So you would put CBr. Then which one's the next most polar? That's D, the phosphorus chlorine bond. Which one's the next? Well, now we're in ionic land here, okay? The boron fluorine would be next. And then the most ionic is LiF. So that's how you would order those. If I said list them in order of increasing polarity, does that make sense? Okay. Now, when we're talking about polar molecules, this just says which molecules are polar. So now we have to consider several things here. 3 things we have to consider. Thing number 1, I'm going to write these over to the side. We have to consider, do we have any polar bonds in our molecule? Okay. Do I have any lone pairs in my molecule? And do I have any, what's the shape? Okay, you need to ask yourself, do we have any symmetry? Here, we're going to be drawing out dipoles, right? Remember what a dipole is? So because PCl is our polar bond up here, let me remind you what a dipole is really quick. Okay, between phosphorus and chlorine, which one was most electronegative? Which element was more electronegative? Well, chlorine was. Chlorine is closer to fluorine. Fluorine's the most electronegative element on the periodic table. So remember these signs, we have the partial positive and the partial, negative. We have to assign those to these elements here. The one that's the most electronegative is partial negative. The one that's least electronegative is partial positive. The electrons in this bond are being pulled towards chlorine. It's more electronegative. That's why the bond's polar. So that's a polar bond. You have to look for that in your molecule. And overall, when a molecule is polar, we can draw a dipole in that does not cancel out. Okay, so that's what we're going to do here. So let's look at sulfur with 2 lithiums, Li2S. What's that going to look like? Well, lithium is main group 1. So very similar to hydrogen, it only has, let's just draw it. It's only got 1 electron that it could technically share, although lithium we think of more as a cation. We don't really think of it sharing electrons, but if we draw a Lewis structure of this, that's what it would look like. And then sulfur should have 2 lone pairs as well. Okay. Now, what do y'all think we should do next here? We need to look at the electronegativities. So lithium is 1, sulfur is 2.5 over here. So what's the difference? Are these bonds polar? So lithium has an electronegativity value of 1. Sulfur we said was 2.5. So the difference is 1.5. Okay. Now that technically classifies it as a polar covalent bond. So we have polar bonds here. So if we were drawing dipoles in, which way would we draw our dipoles? Pointing towards the most electronegative element. Pointing towards your sulfur. Okay, so the lithium is going to be partial positive, sulfur is going to be partial negative, but what do you notice about this molecule? We have symmetry here. So these would cancel out. Now, I'm actually going to be very technical. I think that structure A is more technical than we realize. You want to know why? You want to know what this structure makes me think of? It makes me think about water. Here's what I know about water. Water is very similar. It's an oxygen in the middle, which is also a main group 6 like sulfur. It's 2 hydrogens and those lone pairs. We have not accounted for the lone pairs yet. And when we draw water, we typically will draw it like this with those lone pairs. And remember, those lone pairs are pushing on the structure, and they're pushing those hydrogens closer together. How do we name the geometry of oxygen here? Anybody remember? We could go back to our table really quick. 2 bonded atoms, 2 lone pairs. This is bent. I want you to remember this when you draw a structure. So the way I just drew this lithium and sulfur, I did not even account for the fact that there's lone pairs there. Okay? So we drew it linear. It's not linear, it's bent. Water is like the most polar molecule on Earth. It's so polar, we depend on the polarity of water. And we draw a dipole in with water pointing towards those lone pairs. So we're more correct here if we draw this lithium sulfur structure that same way. Okay, so if we have sulfur, lithium, these are polar bonds. Okay, sulfur is still our polar element here, or our electronegative element, just the way oxygen would be. So we should be able to draw a dipole just the same way. Okay, this is the electron-rich portion of the molecule, and I'm going to put it in blue. These lithiums are the electron-deficient portions of the molecule. Okay, so consider the shape of things too. Consider the geometry when you draw this in. So we can totally draw a dipole in. It's totally a polar molecule. But if you draw it this way, you're going to think, oh, symmetry, it's nonpolar. Okay, but I want you to consider geometries when you write these. This is the correct way to draw it. Okay. All right, let's look at ammonia, NH3. We got a nitrogen, we got a lone pair, and we got 3 hydrogens. Okay. Let's look at a nitrogen-hydrogen bond. Is that bond going to be polar? Hydrogen has electronegativity 2.1. Nitrogen is 3.0. What's the difference there between 2.1 and 3.0? It's a difference of 0.9. And that means it is polar. Okay? So all of these bonds are polar. We could draw in the partial positives on our hydrogens. And we could draw in the partial negative on the nitrogen. And we have this lone pair. Okay, this lone pair automatically is the electron-rich portion. So if we had to draw a dipole in, this is totally a polar molecule. There's no symmetry here, nothing cancels out. We've got polar bonds and we've got lone pairs. We can draw a dipole in like that. So both of these so far are polar molecules. Okay, C, C2H3Cl. How do we draw C? We've got 2 carbons. I'm just going to go ahead and connect our carbons. We've got 3 hydrogens and a chlorine. Can I do this? Can I put all 3 hydrogens on this carbon? And then put a chlorine over here? Can I do that? Anybody have a problem with that? Yes, there's a problem with that. What's the problem? Abby, what do you mean 4?
Carbon has to have 4 bonds, so it
Right.
doesn't work.
This second carbon does not have 4 bonds, so that is an incorrect structure. We cannot draw it like this. I used up all my atoms. I don't have any more atoms. And I can't just put lone pairs on carbon. Carbon does not have lone pairs. Okay? I can't put a double bond like this. What's wrong with if I do double bonds? Well, now this carbon over here has 5 bonds. That's exceeding the octet, and carbon never exceeds the octet. It's not an exception. Okay, so what do I have to do? I've got to take one of these hydrogens off this carbon and put it on this carbon instead. Okay, now neither carbon is satisfied. Oh no, it feels like we took a step backwards. So what can we do?
Double bond the 2 carbons.
Double bond those 2 carbons. I think somebody may or may not be muted. Check that you're muted. I'm getting some feedback. Okay, if we double bond the 2 carbons, now both carbons have 4 bonds.
Come on. Come on.
Okay. We will still need to look at, we've got our structure now. Now we need to look at this. Do we have any symmetry? Do we have lone pairs? Yes, we do on the chlorine. Do we have polar bonds? Okay, so let's look at a carbon. We got a lot of carbon-hydrogen bonds. So carbon is 2.5, hydrogen is 2.1, and I'm looking at the electronegativity chart. So 2.5 minus 2.1, that is 0.4. Is that polar or not? Let's go look at the table. A difference of 0.4 is non-polar, okay, non-polar. So none of these carbon-hydrogen bonds are polar, all right? What about a carbon-chlorine bond? That's the other kind of bond we have right here. All right, carbon-chlorine. Chlorine is 3.0, carbon's 2.5. So that's a difference of 0.5. That is polar. Oh, I'm on my eraser. Okay, this one right here is polar. So we have 1 polar bond and we have a lot of lone pairs. Okay. So looking at this, yes, we got polar bonds. Yes, we have lone pairs. If we put in a partial positive, partial negative signs, I would put in partial negative over here, and all of these would be partial positive. So can we draw a dipole in? 1 dipole that does not cancel? Yes, we can. Across the molecule like that, pointing towards the partial negative side. If you want to move it up here, you You totally can. If that helps. So this one is also polar. I know we're spending a lot of time on this, but these questions are a little more technical. I want you to see they're a little more technical than we think. Okay, so CCl4, that's the last one. The carbon with 4 chlorines. And we just calculated, we know that the chlorine carbon bond is polar. We just identified that right there. All right, we got a bunch of lone pairs on all these chlorines. Okay. So the chlorines are electronegative, and they're the partial negative portion. The carbon is the partial positive. Okay. So can I draw dipoles in? I can. Pointing towards all my chlorines. This structure looks crazy. What do you notice though? Is this someone needs to make sure they're muted. I have no idea. Can everybody please make sure they're muted? This is funny. Someone playing fetch with their dog right now? Hello?
Boy. Good boy.
Okay. I think I figured it out. Well, someone is doing a lot of chemistry with us. All right. So what do you notice what do you notice about this structure? Is it polar or not? Abby said it's not polar. I don't see anybody else shaking their head, but it's not polar because this has symmetry. They all cancel out. So this one is non-polar. All right. Okay. So that was that one. That one took a lot of time. We're about done here regarding how much time we have for lecture. We got about 5 minutes left, but you can see that I had several more questions for review. So what we'll do is if you show up Monday to your lab time, we'll spend time going over these review questions. I would say maybe look at them yourself before then.